The next type of reaction we'll consider is a second order reaction, where the rate law for our reaction, we have minus dA dt is equal to K times the concentration of A squared. Right, so now we have our exponent is equal to 2. And we're just going to, again, consider where it's second order only one specific reactant, and sort of figure things out from here. So we're going to do the same thing that we did for the first order reactions. We're going to say at T equals 0, the concentration of A is equal to some initial value that we're going to call the same thing, concentration of A naught. And we're going to, again, set up our differential equation. We're going to put all the A dependence on one side, all the time dependence on the other. So we will have dA over concentration of A squared is equal to minus KT. Sorry, minus K dt. Okay, and then we need to go ahead and integrate this from our initial condition up to some arbitrary value. So we will integrate from A naught up to A, and integrate from T equals 0 up to an arbitrary T. And when we do this, we can go ahead and solve this integral. On the left-hand side, we're going to get negative 1 over A minus 1 over A naught, because this is the derivative of 1 over x squared. And on the right-hand side, we'll have the exact same thing we did last time, minus KT. Okay, so now we have negatives on both sides, so those will become positive. And this is our rate law. We're going to put we'll put 1 over A on its own on the left-hand side, and that is equal to 1 over A naught plus KT. All right, it did show up. Okay, and this is the equation that describes the behavior of a second order reaction. So no exponential anymore. Now we have like 1 over the concentration dependence. So if we plot, right, so for the first order, we would need to plot natural log of the concentration versus time to get a straight line. Here we would need to plot 1 over the concentration versus time, and that would give us a plot that would give us a slope of k. And unlike the other plot, it would give us a positive slope, right? So k would be positive here. So this would be 1 over our concentration and time along our x-axis here. Okay, and so we have sort of a similar thing, but this is one way to differentiate different types of reactions, different orders, is if you have some concentration versus time data, you can take the natural log, you can take the 1 over the value and plot it versus time and see if either of those gives you a straight line. If the natural log data gives you a straight line, then you have a first order reaction, and if it's the 1 over the concentration versus t that gives you a straight line, then that is equal to, that tells you that you have a second order reaction. And again, this is a way to determine the slope. If you determine the slope, it is equal to k. So this is a way to determine the rate constant for your reaction. One other thing we can talk about with second order reactions, similar to first order reactions, we can think about half-life, right? So defined the same way, we can find what T1 half is, right? And again, that is when the concentration is equal to half the initial concentration. So we can plug that into our formula that we derived here. Say, okay, at A equals A naught over 2, that's going to be equal to 1 over A naught, if all of the strokes come through, plus K times T1 half. All right, it almost all came through. All right, and so then we can go ahead and solve this for T1 half. We will get 2 over A naught on the left-hand side is equal to 1 over A naught plus K times T1 half. And then we can go ahead and solve for T1 half. So we'll subtract 1 over A naught from both sides, and then need to divide by T. So that will give us that T1 half that doesn't need to cross. T1 half is equal to 1 over K times A naught. So unlike for the first order reaction, our half-life here does depend on the initial concentration. So the half-life is not a constant for a given reaction. It depends on how much of it you start with. So the more of it you start with, the smaller the half-life will be. The less of it you start with, the larger the half-life will be. So because it's this 1 over initial concentration dependence. So that's an interesting thing about first order versus second order reactions. For a second order reaction, you do have a concentration dependence for your half-life.